SSC disconnect enable on.
Copy that, ELCOM. All systems are go for entry, descent, landing. Stand by. Stand by.
At the dawn of the 21st century, space agencies in Europe and America began making plans to land the first humans on Mars. But manned missions to the Red Planet have been proposed before. For some, Mars holds the answers to mankind's future in space. Others say Mars is too far, too dangerous, and too expensive for humans to explore. And in a world torn by troubles, some say there is no need, or will, for mankind to reach into space anymore. More than 30 years after the last Apollo astronaut walked on the moon, the American manned space program seems to have lost its way, unable to reach beyond even low Earth orbit.
We've got a problem. NASA has been literally going around in circles with its space program for the past 30 years.
Astronautical engineer Dr. Robert Zubrin has been arguing for years that sending humans to Mars is the mission the space program needs.
It's time that we set goals for NASA that were worthy of the risks of human spaceflight. Mars is the next logical step in our space program. It's the challenge that's been staring us in the face for the past 30 years. It's the planet that's most like the Earth. It's the planet that has on it the resources needed to support life and therefore someday technological civilization. It's the planet that will provide us with the answer as to whether life is prevalent in the universe or exclusive to the Earth. And it's the planet that will give us the critical test as to whether humanity can break out of the planet of our birth and become a spacefaring species.
In the early 1990s, Zubrin was the head of the Mars Direct program at Martin Marietta Astronautics. His team developed a mission to Mars that could be done at a fraction of NASA's projected costs. Using only existing technology, Zubrin argues that the first steps on Martian soil could be made within 10 years.
There is absolutely nothing in this that is beyond our technology.
We are not ready to send humans to Mars right now. We don't know how to keep them alive. There are people out there who say we can go to Mars tomorrow. One of my requirements, one of NASA's requirements, is that if we send humans to Mars, we bring them back alive.
For the past 15 years, Zubrin and his colleagues have waged a campaign to convince society and the political class that humans on Mars should be the goal for NASA now. This is the story of our cold neighboring planet and the debate over whether man's fate is tied to the red world. It's the story of an engineer's journey and the battle of ideas over which direction in space will truly benefit mankind.
We're at a crossroads today. We either muster the courage to go or we risk the possibility of stagnation and decay.
The victor in this debate could determine the fate of mankind. Will we become a spacefaring species? Will we live on more than one planet?
In the winter of 2003, the Chinese put their first taikonaut in space. The Chinese Space Administration plans to begin a manned program of moon exploration by 2017. The European Space Agency has outlined a plan for humans to the moon by 2024 and to Mars by 2033. And the Russians, building on years of experience, are conducting tests for long-duration Mars missions. In America, with the impending retirement of the shuttle fleet and the completion of the International Space Station, the Bush administration announced in 2004 the Constellation Program,
on the moon,
a plan that would return Americans to the moon by 2020. But the program was never fully funded and was eventually cancelled. In 2010, the Obama administration announced its vision for NASA and human Mars exploration.
By the mid-2030s, I believe we can send humans to orbit Mars and return them safely to Earth. And a landing on Mars will follow, and I expect to be around to see it.
With a new timeline for humans to Mars sometime after 2035, and with administrations changing every 4 or 8 years, it is far from certain that such a plan will be realized. 20 years earlier, the first President Bush also proposed a long-term human exploration program, under great fanfare. The program quietly died in Congress a few years later.
If you want to go to Mars, you cannot do it in 30 years. You can't do it in 20 years. You've got to do it in 10 years or less from program start, or you're more or less guaranteeing political failure.
To date, only the Apollo moon program, which was announced in 1961 and had men on the moon 8 years later, has succeeded in getting astronauts beyond low Earth orbit.
I was 5 when Sputnik flew. And while to the adults, Sputnik was a terrifying event, to me, as a child who was already reading science fiction, it was exhilarating, because it meant that this possibility of a spacefaring future was going to be real. And I was 9 when Kennedy gave his speech committing us to the moon.
To go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
I grew up during the 60s when it was Mercury, it was Gemini, it was Apollo. Every month, NASA was doing something more impressive than in the month before. We were going to be on the moon by 1970, Mars by 1980, Saturn by 1990, Alpha Centauri by the year 2000. We were moving out, and I wanted to be part of that. And so I got myself a scientific education. But then in the early 70s, it's all collapsed. We achieved the first part of that program, moon by 1970, but the Nixon administration shut down the rest, and we did not move out into space. And for a while, I accepted that, grudgingly. I became a science teacher. But then in the early 80s, something hit me, and I said, I'm not going to accept myself doing less than what I had dreamed of doing when I was a boy.
Zubrin went back to graduate school, getting advanced degrees in engineering and aerospace. He then went on to work at Martin Marietta, which later became Lockheed Martin, designing interplanetary missions. It was here that Zubrin's obsession with the Red Planet began to take hold. While at Martin in the 1990s, Zubrin and his colleagues developed a plan for sending humans to Mars that changed NASA's thinking on the issue. But the plan has languished on the drawing boards ever since. Now, as president of the Mars Society, Zubrin is at center stage in the debate over the future of manned spaceflight. Known as a smart, visionary scientist, he has authored several books on exploring space and is the self-appointed spokesman for the possibility of colonizing Mars.
Mars is where the future is. Mars is the closest planet to the Earth that has on it all the resources needed to support life and therefore technological civilization. It has water, it has carbon, it has nitrogen, it has a 24-hour day, it has a complex geological history that has created mineral ore, it has sources of geothermal energy. Mars is a place we can settle.
One reason for such optimism over a frozen world like Mars is evidence that 2 billion years ago, Mars was a much warmer and wetter place.
We think that at one time in the ancient past, Mars was very similar to the condition of early Earth.
This Martian warm age lasted for over 1 billion years and could have been a suitable environment for the development of life.
If we go to Mars and find evidence of a second genesis on Mars, I think we can conclude that the universe is full of life. We can probably conclude that on some planets that life evolves to more complex forms, and I think we'd be reasonable to conclude that intelligence could also emerge on some planets as well. It really does answer the question, are we alone? And that to me is a question that transcends science. It's a philosophical, societal, as well as scientific question. To me, that's the big prize. That's why Mars is interesting. That's why human exploration makes sense.
Space programs are often criticized for the huge sums of money they require. Although the American space program is less than 1% of the federal budget, a human mission to Mars may have to wait for better times.
There are those who say that we have many problems to deal with here on Earth, and we need to postpone ventures such as the human exploration on Mars until these problems are solved. Well, there were many problems in Spain in 1492, and there still are. There are problems that need to be dealt with here on Earth, and should be dealt with. But we also have to think of the future. We also have to think about opening up new volumes in human history. I believe that it's essential for a positive human future that humanity expand into space. The greatest value that we got out of Apollo was the creation of intellectual capital through the inspiring of millions to go into science and engineering to be part of the great adventure of human expansion into space.
There's a phrase that happened with the Apollo program, which was, if we can go to the moon, we can, and then everybody's filled in whatever they were interested in. Build mass transit, cure cancer, do this, do that. The point is, it did give us a sense that we could accomplish great things. It did bring out the best of us.
We excited a generation of engineers and scientists. The generation that built the computers and cell phones and all the technology everybody uses today and takes for granted.
If we set humans to Mars as our goal, we'll get millions of new scientists that will create new inventions, new industries. This is the enormous payback, and we can get it if we set the kind of challenge that will inspire the youth.
To Zubrin, civilizations, like people, thrive on challenge and decay without it.
We have everything we have today because of our predecessors who had the courage to leave the world of the known and go out into the wilderness and build new cities. And if we stop being people like that, then we will hand down much less to our posterity than our ancestors handed down to us. So there's the choice in life. One either grows or one decays. Grow or die. I think we should grow.
History proves that we have never lost by pressing the limits of our frontier.
In the summer of 1989, the first President Bush announced the Space Exploration Initiative, directing NASA to draw up long-term plans to get humans back to the moon and begin developing a program of manned Mars exploration. At Martin Marietta, Zubrin and his colleagues looked forward to moving NASA's space program outwards after 2 decades in low Earth orbit.
Of course, we were very excited when Bush made his call saying that he was making a national commitment to implement such a program.
NASA assembled a large team to take on the space initiative. In 90 days, the team developed a 30-year plan that required an enormous buildup of space infrastructure.
What the NASA bureaucracy decided to do was basically design the most complex mission they possibly could in order to make sure that everyone's pet technology would remain mission critical, which is the exact opposite of the correct way to do engineering.
First, NASA would triple the size of the planned space station and add enormous hangars, as well as free-floating fuel depots, checkout docks, and crew stations. Then, on the moon, they would construct more shipbuilding facilities, bases, and depots. Next, the moon crew would construct the Mars ship, a huge craft dubbed by its detractors as Battlestar Galactica. This ship would carry everything to Mars over an 18-month flight. Once in Mars orbit, a small group would descend to the surface, spend a few days, then plant a flag in the ground and go home. The plan became known as the 90-day report.
To those of us at Martin who had been engaged in designing Mars missions, when they saw the monstrosity of complexity of the 90-day report, we were dismayed, and it was readily apparent to anyone with any insight that that program would fail politically.
The plan was submitted to Congress. The estimated cost, $450 billion. The legislators went into sticker shock. This would have been the single most expensive program for the United States since World War II. By the end of 1990, Congress had refused all requests for SEI funding. When the realization came that SEI was doomed, Zubrin wrote a memo to his colleagues at Martin Marietta, outlining his problems with the NASA plan and arguing for a more direct approach. Zubrin favored launching a Mars mission directly from the surface of Earth, using only existing rocket technology. This negated the need for a lunar base and avoided the complexity and cost of building ships in space. He also objected to NASA's plan for a short surface stay on Mars, a mission that would amount to little more than a flag and footprints exercise. To Zubrin, we were going to Mars to explore and develop a new world. To maximize surface time, Zubrin proposed using a faster flight path, known as a conjunction-class mission. This would mean a crew could arrive on Mars after only a 6-month journey. They would then remain on the Martian surface for a year and a half. This would give the team time to explore a wide area and conduct detailed research about the planet. Then, as the Earth return window opens, the crew would launch from Mars for the 6-month trip home. Zubrin was convinced that a simplified, more robust and cost-effective mission could be designed using these principles. Along with several like-minded colleagues, Zubrin decided to ask management at Martin to allow them to design alternative Mars missions.
The management approved that, and we formed a team that was known as the Scenario Development Team of just 12 people from the whole very large Martin company.
One team member, whose thinking was closely aligned with Zubrin's, was David Baker.
I went off to my office and said, all right, how would I do a Mars mission if I had to pay for it and I had to go on the ride? And I said, well, it's going to be simple. There's going to be no on-orbit assembly. I really tried to take everything out of the mission that didn't absolutely need to be there.
While the rest of the team focused on longer-term, more traditional mission plans that required on-orbit assembly, Zubrin and Baker decided to collaborate on a mission that could be done near-term.
We decided to do Mars the way Lewis and Clark did America. Okay? Use the local resources, travel light, live off the land.
Zubrin and Baker were convinced that a Mars mission could be launched directly from the ground. The other team members felt this was impossible, that the weight of the rocket fuel required for a round trip to Mars was so enormous it would render the launch ship impossibly heavy. To solve this problem, Zubrin was exploring a radical idea that had been kicked around the aerospace industry since the 1970s. The idea was to produce a methane-oxygen rocket fuel directly from the Martian atmosphere. It was a relatively simple and robust chemical engineering procedure that was done commonly in the 1800s, the era of the gaslight. If the idea worked, astronauts could land a relatively light ship with empty tanks. They wouldn't have to ship all the fuel with them for their return trip. This would radically lower their size and weight. The only problem was methane-oxygen fuel requires a hydrogen component. Hydrogen exists on Mars in the form of H2O, but water may be difficult or impossible to extract from the Martian environment.
Really, the hydrogen was only 5% of the total weight of the methane-oxygen propellant being manufactured. So if you just say, okay, we won't be pure, we won't get all of the propellant from Mars, we'll just get 95% of the propellant from Mars. The other 5%, the hydrogen, we'll just bring from Earth.
Another fundamental resource that could be extracted from the Martian environment is oxygen. A second processing unit could separate oxygen molecules from the thin carbon dioxide atmosphere, providing breathable air for a Mars crew.
If used intelligently, the same resources that make Mars interesting are precisely what could make it attainable.
Baker and Zubrin had greatly reduced their mission mass, but they still found their ship was too heavy and would require 2 launches and assembly in space. Then Zubrin hit on an idea.
Well, one of the key events of the Mars Direct development was one morning Bob burst in my office and said, "I've got it."
The idea that I finally hit on in 1989 was that we would split the mission up into 2 parts, and we'd send the return vehicle out first with its own return propellant plant. So the propellant would be made on Mars before the first astronauts ever left Earth.
With 2 separate direct-to-Mars launches, a human crew would have a fully fueled ship waiting for them on the surface of Mars before they ever left Earth. So Zubrin and Baker had come up with a plan that seemed to accomplish all of their goals. It was relatively inexpensive, development time was short, they could use existing technology, and it allowed for a long stay on the Martian surface. They dubbed their idea Mars Direct.
SSC disconnect enable on. 35. Let guys go. Hydraulics go.
Aboard an Ares rocket is the Earth Return Vehicle, or ERV. No one is aboard this ship. It will pave the way for the astronauts who, years later, will use the ERV to return to Earth.
1. And liftoff.
On its second day, the ERV deploys a small nuclear power reactor. The reactor powers a chemical plant inside the ERV. the plant will produce the methane oxygen rocket fuel for the launch home. Nearby, a second robotic rover is guided to a pre-picked landing site for the human crew. It places a radar transponder to help guide the astronauts in. The long journey to land a human being on Mars begins.
3, 2, 1, engines.
Carrying the most skillfully assembled flight team in history, 4 astronauts begin their 2.5-year mission to the Red Planet. This will be the first time a human has gone beyond the Earth-Moon system, 250 million miles farther than any person has ever been. To counter the health problems of zero gravity and to fully acclimate the astronauts to Mars, the ship will deploy a weighted tether attached to the last stage of the spent rocket booster. By thrusting the ship into a rotational spin, the counterweight of the rocket will create centrifugal force and thus artificial gravity. The crew will be able to live with their feet planted firmly on the floor during their 6-month transit. But the HAB is not entirely alone on its journey. Just ahead of it is a second ERV, identical to the first. Launched just a few weeks prior to the HAB, it will prepare the way for a second human crew that will follow 2 years later. It can also function as a backup for the first mission, if anything should go wrong. On the 6th month of the flight, the crew will gaze upon an alien world. This is the new frontier.
Oh, spectacular. Just spectacular.
After days in orbit and satisfied with the landing conditions, the crew will receive final word from Mission Control on Earth.
All systems are go for entry, descent, and landing. 3, 2, 1.
It will be a tense 40 minutes before people back on Earth get the signal from Mars and know if everything has gone well.
Okay, 75 feet. Car's looking good. Down a half. Pitch forward. 60 seconds. Lights on. Forward. Forward. 40 feet down. 2.5. Big shadow. 4 forward. Drift into the right a little. 30 seconds. Forward. Contact light. Okay, engine stop.
We're seeing it on the LTP. We're on Mars, everybody.
For more than 500 days, the astronauts will live on Mars and embark on one of the greatest journeys of discovery in the history of science. Will they find life? Or the fossilized remains of past life? Such a discovery could tell us whether our solar system has seen more than one Genesis, and answer the ultimate question: are we alone? In any case, these explorers will be learning how feasible the colonization of Mars really is, and whether or not mankind has a future among the stars. Then, when the time comes and the window for Earth return opens, the crew will climb into their Earth return vehicle and head home. They will arrive home heroes, the first to stretch the limit of man's expanse from one planet to another, their names added to the list of great explorers of new worlds. In their footsteps, others will follow. What began as a trickle is free to rise into a deluge of humankind, sweeping over a once barren land and transforming it into a viable new world. When Baker and Zubrin presented Mars Direct to their bosses at Martin, they expected the worst. To their surprise, management was excited about it. They liked the fact that everything needed was relatively simple and near-term.
As time went on, Martin Marietta embraced Mars Direct as their creation and put Bob and I on an airplane to several NASA centers to present Mars Direct and try to build some momentum for it.
Baker and Zubrin flew to the Marshall Space Flight Center in Huntsville, Alabama. This had been one of the original design hubs for the Apollo moon landings, but recently many of the engineers had become demoralized by the failure of NASA's SEI program. Tag team style, Baker and Zubrin presented their alternative mission architecture. The response was thrilling. The old-school Apollo crowd embraced it. This was a plan that actually made sense and was within reach.
Baker and I gave a number of briefings. The first was at the Marshall Space Flight Center. Next was at Johnson. These people were incredibly excited.
Over the next few weeks, Zubrin and Baker were flown around the country, pitching to all branches of NASA. And everywhere they went, the response was electric. The plan was standing up to scrutiny, and groups all over NASA were converting to Mars Direct. Their tour culminated in a public presentation to the National Space Society. The crowd gave the two aerospace engineers a standing ovation. A week later, the story was in newspapers around the country. But a counterattack was beginning to form within NASA. The space station teams and many in the advanced propulsion groups were against the idea. Since Mars Direct didn't need their programs, they felt under threat. As quickly as doors opened for Zubrin and Baker, they began to close.
NASA didn't want to pursue a Mars mission at that time. They didn't want to be derailed by a bunch of Mars fanatics that thought that their idea of what NASA should do should overwhelm what NASA thought NASA should do.
What we did in Mars Direct was literally come up with the leanest solution, the one that involved the least spending on an assortment of technologies and infrastructural elements, including, for example, we made no use whatsoever of the International Space Station. And so people involved in all those programs were very upset because we were showing that you could go to Mars without their program being required. And they felt that we were de-justifying them.
The NASA administration rejected Mars Direct. The two engineers were outsiders again. But Zubrin remained determined.
Bob had grabbed hold of it, and I could see that it was his, and no matter what I did, he was going to do what he was going to do. And he was going to be a proponent for it and push it, and I really saw my role sort of evaporate. It's a little bit like being a dim planet next to a bright star around him in terms of his enthusiasm, and you really can't compete with that. All you can do is decide how you're going to deal with it.
By February 1991, Baker quit Martin to start his own firm. Zubrin battled on. For the next year and a half, Zubrin tried to get NASA to pay attention, giving speeches, writing papers, but Mars Direct's time seemed to have passed.
But then in 1992, a new administration came into power at NASA, and Zubrin saw a second chance.
I was invited to brief Mike Griffin, who was the Associate Administrator for Space Exploration in charge of the whole Space Exploration Initiative. He immediately became a very strong supporter of Mars Direct.
But before the engineers at NASA would take another look at Mars Direct, they wanted Zubrin to prove that producing rocket fuel on Mars could work. They gave Martin Marietta a small budget to do an experiment. Zubrin and his team built a machine called the In Situ Propellant Plant. It could take carbon dioxide, the dominant gas in the Martian atmosphere, combine it with a little hydrogen, and produce a methane-oxygen fuel.
We did it in 3 months with a very small team. We built a plant that was 94% efficient, and no one who actually participated in that effort was actually a real chemical engineer. They were all aerospace engineers, like me, who were simply dabbling in chemistry in order to prove to NASA that 19th century chemical engineering really worked.
With the experiment a success, the administration had Zubrin give detailed briefings of the mission plan to the engineers at the Johnson Space Center. They liked it, but had some problems. Dave Weaver was the lead mission architect.
There were a number of things that we were concerned about with Bob Zubrin's mission. First of all, we thought his estimates of mass were probably too optimistic. Didn't have sufficient margins for a variety of things, not the least of which would be things like provisions for the crew, the amount of water that would be required. We thought his ascent vehicle was very large, which meant his power requirements, his propellant requirements were much larger than needed to be. His trip times out were too long, and that for very little effort you could get them shorter. The other problem was the size of his crew. He had a 4-person crew. I think virtually every study that's been done says that a 4-person crew for a 3-year type of mission is probably not realistic.
Weaver took Zubrin into his office, and the two men worked out compromise mission architecture. First, Weaver wanted 3 launches for every mission instead of 2. The first year, 3 ships would launch: a MAV, Mars Ascent Vehicle, an unoccupied HAB, and an ERV, Earth Return Vehicle. The HAB and MAV would land on the surface and begin producing fuel for the return flight and air for the crew. These craft would spend 2 solitary years on Mars, allowing NASA to test all of the systems before sending a human crew. Then, in the 3rd year, 3 more ships would launch, this time with the HAB occupied by astronauts. The other 2 ships are for a future mission, and less needed as a backup for this crew. Once on Mars, the team could also utilize the first HAB. Then, after a 1.5-year stay, the crew would climb aboard their small capsule and rendezvous with the return ship. This ship would carry them back home in a roomier environment than Zubrin's ERV. Zubrin called the plan Mars Semi-Direct. NASA called it the Design Reference Mission.
They had a larger crew than we had. They had bigger ships. They had more equipment. They had heavier equipment. So they had to do the mission in 3 launches instead of 2, but it was done with the same principles of Mars Direct.
The plan was subjected to the same cost analysis that tagged the 90-day report with a $450 billion price tag. The Design Reference Mission came back at a fraction of the cost, $55 billion. Spread out over 10 years, it could be done within NASA's existing budget. The plan made the cover of Newsweek. Here was a mission architecture that was affordable and could be done today with existing technology. But NASA's astronauts have not left low Earth orbit since.
With the completion of the International Space Station and the retiring of the Space Shuttle program, a debate rages over the future of space exploration.
Should NASA continue to focus on low Earth orbit, developing technologies for the future? Or should NASA have a goal, like it did in the 1960s with Apollo?
The way we got to the moon was by a presidential imperative that demanded that NASA get to the moon within a decade. So NASA was forced to sit down, design a plan for how to do that, and then fly the mission. Since that time, without the presence of a driving imperative, we engage in basically a random set of constituency-driven programs which are justified ad hoc afterwards by the argument that they could prove useful at some time in the future when you actually have a plan to go somewhere.
I think NASA has focused on a steady process where the government can't just pull the plug on their funding. I think the Apollo cancellation was very traumatic for NASA, and it really transformed NASA from what it was in the 60s to more of what it is now. If you have a singular program like going to Mars, then it is very vulnerable to having its funding pulled.
NASA must be destination driven. It is the only thing that allows the agency to be productive. NASA was 100 times more productive when it was destination driven than in the period that it has not been. And we have stagnated in NASA since 1973. 30 years, more than a generation, has been wasted. The American space program's been stagnant for 30 years. There's a once-in-a-generation shot right now to get it moving again by giving it a goal that'll take it somewhere. So the stakes today are high. And if you ask me if I am nervous right now, I am.
Dr. Zubrin.
Why is NASA stuck in low Earth orbit? The problem with NASA's lack of current achievement is not money. The problem is lack of focus, it's lack of a goal. It shouldn't be humans to Mars in 50 years. It should be humans to Mars in 10. We can do this. We do not need gigantic nuclear electric spaceships to send people to Mars. That is pork, it's nonsense. The primary question I get from the American people is, why aren't we doing this? There's a big sense of disappointment, almost verging on a sense of betrayal. The purpose of spaceships is to actually travel across space and go to new worlds, not to hang out in space and observe the health effects from doing so.
Dr. Zubrin, in your testimony, you were very passionate on it, but you also were mad. You're mad we haven't done this, or that this vision has been stolen from a generation?
I guess you could say that. It's like Columbus coming back from the New World and Ferdinand and Isabella saying, so what, forget it, burn the ships. Okay, that's what has happened in this country. We've won our point that there needs to be a destination. The point we need to win on now is that the destination needs to be Mars, and it needs to be soon.
The movement to send humans to Mars in the near term began at the University of Colorado in 1978. A graduate student in astrogeophysics named Chris McKay gave a small seminar on the possibility of introducing life to Mars.
I got interested in Mars in graduate school. I entered graduate school the same year that Viking landed on Mars and sent back these images, and it sent back data that showed all the elements needed for life are here on this planet, and yet there's no life here. I don't know, that's odd. It's sort of the lights are on and nobody's home. And I thought, well, that's curious. So some of my other grad students and I, we sort of got together to talk about, well, if there's no life on Mars now, could we put life there? And that evolved also into the question, well, maybe there was life in the past, and we could find fossils, evidence of it. Well, how would you do that? Well, you do that by sending people there.
Together with fellow graduate students, the group decided to put together a small conference to discuss the matter of human Mars exploration.
We basically just started a forum. We invited everybody from all the NASA centers and from all the universities that were involved in it, and they all came. And it really was, in retrospect, I realized a very important step toward building a consensus for human exploration of Mars.
In 1996, I published my first book, The Case for Mars, and the response was phenomenal. I got 4,000 letters from all over the world. I had Parisian bankers and 12-year-old kids in Poland and firemen from Saskatoon and astronauts, and they're all writing me and saying, how do we make this happen?
Bob Zubrin came to the third Mars conference and got very much involved. And he was willing and interested in forming a society, forming a group and organizing.
He said, look, if we could pull these people together, if we can get them to work together, we could have a force that could actually make humans to Mars happen.
The group formed the Mars Society. Robert Zubrin became the president. They held their first convention in 1998.
The convention was just magic. We had no idea how many people were coming. They were there not just from the United States and Canada and Europe. They were there from Israel. They were there from Mozambique. They were there from New Zealand. It was astonishing.
Since its inception, the Mars Society has attracted members worldwide.
Derek Shannon is the head of the Southern California chapter. He's met with political leaders from all over the country.
If you make them look at the whole Mars vision in historical terms, it becomes a much easier sell. How will the Martians remember our century? They're probably not going to remember our deficit, our wars, our healthcare. Those will be footnotes. What they'll remember is that out of all of human history, there came a generation that decided to take this amazing step out into space. And if you tell politicians that they're the ones whose names actually get to be remembered, that's when, hopefully, the space program starts going somewhere.
In order to further the knowledge necessary for a manned mission to the Red Planet, the Mars Society has been building research stations around the globe, all of them based on the design of Zubrin's HAB module. Most recently, the Society set up a desert research station in Utah. Here, international researchers and aerospace students come to do experiments under the harsh desert conditions and learn what's necessary to keep a Mars crew alive and productive.
Basically, what we're doing here is undergoing analogue studies. Crews of up to 6 people at a time come together to live in a full simulation environment for up to 14 days. So what that means is every time we go outside the HAB, people have to don spacesuits. They have to depressurize. When we go outside, they're called extravehicular activities. They can only be of a certain duration due to the air supply. We have to recycle all our water and basically have our own food as well.
It's great to fantasize, but it's another thing when you have to put it together, when the nuts have to fit the bolts.
Like the Apollo missions to the Moon, sending human beings to Mars will mean putting people in harm's way. There are many dangers in outer space, and many things could go wrong. A serious equipment breakdown could doom the crew to their deaths. Some argue that the risk of failure is simply too high.
You know, back in the days when medieval man was looking out from Europe and thinking about exploring the world was unknown, and map makers populated their maps with dragons. We've got the same thing today. There are people who are afraid to go out into space, and they've populated their maps of the solar system with dragons. You know, we've got cosmic radiation, we've got zero gravity, we've got back contamination. But these are dragons that we can take on.
There are two kinds of radiation astronauts must contend with in outer space: solar flares and cosmic rays. Solar flares are floods of protons that burst from the sun at irregular intervals and would be dangerous to an unshielded human crew.
We are not ready to send humans to Mars right now. We've got to know a lot more about radiation and radiation mitigation. One of the Apollo flights barely missed, like by a week, a major solar event. If it had gone off when the Apollo astronauts were on the way back and forth to the moon, they would have gotten their entire lifetime radiation dose in that one mission. And that's just one solar flare. So that's why we worry about this.
In the Mars Direct plan, Zubrin envisions a central, insulated core where a crew can retreat to while the radiation passes by. The core would be surrounded by all the provisions of the mission. This should stop any harmful dose of radiation from reaching the astronauts.
Basically, you use your pantry as your storm shelter. So a solar flare happens, the alarm bell rings, the crew goes into the storm shelter, they stay in there cramped up pretty tight for a few hours until the all clear rings and they come out. This is going to happen once, it might happen twice in the course of the mission.
The second type of radiation is cosmic rays. This constant rain of charged particles comes from interstellar space and cannot be avoided without many meters of shielding. We can experience some of this type of radiation on Earth at high altitudes. Airline pilots who spend their careers flying high in the atmosphere can receive almost as much of this radiation throughout their life as a Mars astronaut would on a 2.5-year mission.
It's a long trip. It's a 6-month trip there, a 6-month trip back. It's probably a year on the surface. That's a lot of radiation.
The best estimates are that the magnitude of that dose is not that great, perhaps 60 rem of radiation scattered over 2.5 years. Now, 60 rem of radiation delivered over a long period of time like that would not create any noticeable effects at all. It would, though it is believed, increase your statistical risk of getting cancer at some point later in your life by about 1%. Right now, if you're an average American and you do not smoke, you have a 20% chance you're going to die of cancer. This would make it 21. If you're an average American smoker, it's 40. So in fact, if you recruited the Mars crew out of smokers and sent them to Mars without their tobacco, you would be reducing their chance of getting cancer.
With the immense distance from Earth, never before experienced by a human being, with the constant dangers of outer space surrounding their small, life-sustaining craft, and with nowhere else to go, the psychological impact on a crew could be severe.
Fear is real. I mean, it would be, to me, abnormal for a person to not feel the fear of getting on a rocket and launching into space and going to Mars. So I think fear is a very normal thing that all astronauts, in fact, are supposed to have. And I would be afraid to fly with someone who does not have fear.
Some psychologists worry that cabin fever could set in, and the crew might literally go crazy.
The human Mars mission is a more rigorous and difficult condition than most of us experience in daily life. But it is hardly a more difficult situation than many people have endured throughout human history. We could compare the Mars crew to the crew of 19th century or prior sailing vessels, many of whom were away from home for 3 years or more than 3 years, under conditions in which they're eating extremely bad food, without any medical knowledge to support their health, commanded by brutal officers. In every respect, the crew of a human Mars mission, with the full support of mission support and the whole world cheering for them and great rewards awaiting for them in life upon their return, is in a vastly superior condition.
The Mars Direct crew will spend most of their time inside the 2-story HAB, carefully designed to promote psychological well-being despite the confinement.
The space where I think everybody would spend the most time, just like a lot of homes on Earth, would be the galley wardroom area. There would be chairs, a table, some kind of large screen for entertainment. You would have individual staterooms about 4 or 5 feet wide. The ability for them to communicate with loved ones, with colleagues on Earth, I think will be almost unlimited.
A Mars crew will need to be carefully chosen and thoroughly tested to ensure their ability to handle the extreme isolation.
Wow, what a place. What a view, isn't it, John? It's absolutely unreal.
John Young, who went to the moon, used to say that he could cover the Earth by just lifting his thumb up to it. And he says that when you go to Mars, you are going to redefine the concept of loneliness. And so it is very important that the crew be well balanced and well chosen so that they can support each other.
Whoever gets picked to go, they will have to learn to live together for 2.5 years.
If you put out a call for volunteers for the first crew to Mars, they'd be lined up coast to coast. Most people recognize what's left after you go is the good you left behind. And to take part in an adventure of this character, of such a historic character, of extending the reach of the human species, this is something of immortal significance. One of the most bogus threats associated with the Mars mission is the so-called back contamination issue, which is this notion that you go to Mars and discover these virulent disease organisms that you bring back to Earth and destroy all life on Earth.
If we discover life on Mars, One fear is that our Earth biology will have no defense against possible Martian pathogens. Some argue that missions to Mars cannot be risked until we can prove Mars is free from harmful contaminants.
This is completely nonsensical. There's natural transfer of material from Mars to Earth all the time. We get around 500 kilograms of unsterilized Martian rocks landing on Earth every year, and they have been doing so for the past 3-4 billion years. And so if there were Martian organisms that could contaminate the Earth, they've already done so.
Although the prospect of Martian diseases seems remote, lawmakers have required that NASA create elaborate protocol to ensure that any extraterrestrial material stays contained. And like the Apollo astronauts, who spent 17 days in quarantine after their return from a sterile moon, a Mars crew will have to be thoroughly tested for any harmful Martian pathogens.
The probability is infinitesimally tiny. But nevertheless, this is our home planet and it's extremely important and we have to protect it.
The idea of a pathogen on Mars is clearly ridiculous because there is no megafauna or megaflora on Mars for pathogens to infect. So it is impossible to propose a credible life cycle for a Martian pathogen. The diseases that afflict us have been co-evolving with us and our ancestors and near relatives for the past 3 billion years, and they are specifically designed to live inside the habitat of the human body and to overcome its defenses, and they've been engaged in an arms race with the human defenses for those 3 billion years. This is why humans do not get diseases from distantly related species. For example, I don't know of any person who has ever contracted Dutch elm disease, and trees don't get colds.
When the first Mars lander touches down, the crew will be staring out at a new world, a place that in 4 billion years, no eyes have ever seen. The crew won't be alone. Millions of television viewers back home will be watching as the first man or woman places their footprint into the rust-colored soil. The crew will savor these moments, for here, someday, a new branch of civilization might begin, and future Martians will remember and celebrate this day. There is much for the crew to do and explore. One of their main mission objectives will be to search for signs of microscopic life. To do this, they will follow the ancient water flows. For on Earth, where there is water, there is life. To help the crew in their search, they will have a pressurized rover that allows them to explore in a comfortable shirt-sleeve environment. This means the crew can examine a vast area around the landing site during their 18-month stay. And there is much to explore. Mars has 58 different kinds of topography and a surface area equivalent to all the continents of Earth combined. If these explorers can uncover the fossilized remnants of indigenous Martian life, they will redefine mankind's understanding of its place in the universe.
For if life arose separately on a planet so close to our own, it strongly suggests that the universe is a biologically rich place and full of life. For some, the ultimate question of Mars, though, is will there be human settlements on the planet? Will Mars become a new branch of human civilization?
As each subsequent Mars mission explores a wider and wider area of the planet over several years, an ideal site for a base will be found. probably one with a thermal vent that can supply water and power. At that point, several HABs will be landed in this one spot, with crews that plan to stay for 4, 8, or even 12 years. The HABs will be interconnected, and a permanent human presence on Mars will be established. This scientific community will have to learn to become self-sufficient, to be able to survive on Mars without supplies constantly being sent from Earth. But unlike any other planet in the solar system besides Earth, Mars has all of the fundamentals needed to make this possible. Its 24-hour and 37-minute day is critical for growing plants. It has all of the elements necessary for creating building materials like plastics, metals, and glass. And it has oceans of water frozen into the soil.
If we can develop this craft of living on Mars, then Mars becomes inhabitable. Not immediately physically, but intellectually. I mean, look, what determines whether an environment is habitable or not? Is Colorado habitable? We're not naturally adapted to live in Colorado. We're tropical animals. No one could survive a single winter night here without technology, such as clothing, efficient use of fire. We invented our way into becoming people that could colonize such hostile environments.
Eventually, with a lot of ingenuity and invention, the scientists will learn to live off the land. They will grow crops in the iron-rich but potassium-poor soil. And they will produce oxygen and energy from the water and atmosphere. Sooner or later, children will be born, the first true Martians. They will grow up to see Mars as their home. With time, more and more people will arrive. These won't only be scientists, but settlers, people who plan to stay. They may come for all kinds of reasons, but to them, Mars will be a chance to start over, to build a new life for themselves.
The well of human social thought is not exhausted by the present age, and I don't think will ever be exhausted. There will always be people with new ideas on how humans should live together.
With Mars so far away, the hold of Earth governments on their colonies will be tenuous. The Martians will need to govern themselves.
Mars is not going to be a utopia. Mars is going to be a lab. It's an open frontier. It's a place where things are going to be tried out. I think we'll see a lot of noble experiments on Mars. Perhaps some of these Martian colonies with their novel ideas based on the best thought the 21st century has to offer, maybe they'll find ways in which humans create society that are more humane and offer more opportunity for human potential.
The ultimate dream of the Martians will be to terraform their planet, to make Mars as hospitable as Earth. This may not be as big a fantasy as it seems.
Here we are on Earth, a world that's very sophisticated and developed and complete. And anything we do is just a subtraction. It's because we live in such a biologically rich planet. When we go to Mars, we have an opportunity that we don't have on Earth. Here's a planet that's died. Here's a world that's not full of biology, probably doesn't have any at all. Well, there, we can actually do something to help.
Once there are large human settlements on Mars that will have significant industrial capability, we could actually start addressing ourselves to the question of transforming the Martian environment itself, terraforming Mars, as it's called, because Mars was once a warm and wet planet, and it could be made so again through human engineering efforts.
With daytime temperatures in the Martian tropical zone averaging around 0 degrees centigrade, and with an atmosphere only 1% as thick as Earth's, exposure to these elements by a human without a spacesuit would be instantly fatal. The first step to terraforming Mars and bringing it back to life will be for the Martian colonists to warm up their planet.
Well, we know how to warm up planets. We're doing it on Earth. by putting gases in the atmosphere. On Earth, it's not a good idea to warm up the planet. The temperature was just fine, thank you. We don't need it any warmer here. But in principle, if you could trap the sunlight reaching Mars today, every single photon that's hitting Mars, Mars would warm up in about 10 years. Well, obviously you can't trap every single photon that's hitting Mars, but you can trap about 10% of them with the greenhouse effect. So that would imply that Mars could warm up in about 100 years. Well, 100 years is a long time, but it's not astronomically long.
One idea is to build small, automated factories that produce super greenhouse gases with no ozone-depleting side effects. Although these gases would be unwelcome on Earth, for the Martians they would be an efficient way to trap heat.
Then within a few decades, we would raise Mars by more than 10 degrees centigrade. And if you did that, that would cause massive amounts of carbon dioxide that is currently adsorbed into the Martian soil to start to outgas.
Carbon dioxide is also a natural greenhouse gas. As it builds up in the atmosphere, more and more heat will be trapped, which will in turn cause more CO2 to outgas. The process will become automatic, and as the atmosphere thickens, Mars will eventually reach a state of equilibrium and stay warm naturally. The rise in air pressure would mean that the human colonists could discard their pressure suits and walk around the surface of Mars carrying only a supply of oxygen. And as the temperatures rise on Mars, water frozen into the soil will begin to melt out. And for the second time in its history, Mars would have liquid water on its surface. Dry Martian rivers will start to flow. Seas will rise, and there will be rain clouds in the skies. The return of Mars to its warm and wet stage will make it a fertile environment for life. Any indigenous Martian organisms lying dormant will begin to grow, and Mars will be full of Martians. If no native life emerges, or that life is all dead, then humans could begin addressing the idea of bringing life from Earth. At first, it would be simple organisms, perhaps genetically engineered, that would thrive in the Martian environment. Then more complex plants could be introduced. The plants would be right at home in the carbon dioxide atmosphere, and with no competition and a whole planet to cover, they could transform Mars into a green world. Warming Mars so that it sustains life is rapid, but then the slow process of making the atmosphere breathable for humans and animals starts, and that's done by plants. Although the process will happen naturally, if the colonists can't find a quicker way, it will take tens of thousands of years.
This is a philosophical debate. Many people think the universe has a big sign on it that says, "Do not touch." Leave it alone. It was made this way. It is not in our purview as human beings to change anything. I can respect that view, although I disagree with it. I think the universe has a big sign on it that says, "Go forth and spread life." Because when I look around the universe, I think life is the most amazing thing we see. It is just incredible. And we human beings are uniquely positioned to help spread life from this little tiny planet, which it seems to have been started on, beyond. And that's our gift. Earth's gift to the universe, I think, is the gift of life.
This scheme for terraforming Mars is based on 20th century notions of engineering. I don't think it is how Mars will actually be terraformed. What you have here is a 20th century mind trying to address a 22nd century problem. And so I think Mars will be terraformed by the 23rd century, not by the 33rd, by the 23rd. Things that would seem utterly fantastical to us is how it will actually be done. But it'll be done. We're at a crossroads today. We either muster the courage to go or we risk the possibility of stagnation and decay.
The exploration of the solar system and expanding of life through the rest of our solar system and someday beyond is the kind of thing that will keep our civilization going.
We're explorers by nature. Eventually we will go to the stars. And the question is, when will we start?
I think a man-Mars mission could happen within 15 years.
Some days I'm very optimistic. I think we can do it in 10, maybe 15 years. Other days I see all the political things that go into the space program. I look back on the 30 years we've been bogged down, and I get more negative about it, and I say it's going to be another 3 decades or 4 decades.
I would be surprised if we got to Mars prior to 2025 or 2030.
In May of 2018.
Understanding the various political obstacles that exist and what we need to fight through to get the program started, I believe that we will be on Mars by 2020. You have to believe in hope. You have to believe in the future. There are more and more people coming around to the point of view that a positive future for humanity requires human expansion into space. We will eventually break through the forces of inertia that have been holding this thing back.
Time is flying by on this busy, crowded planet. As life changes and evolves from second to second. At the same time, the arc of the human lifespan is getting longer. 67 years is the global average, up from just 20 years in the Stone Age. Modern science provides a humbling perspective. Our lives, indeed even that of the human species, are just a blip compared to the Earth, at 4.5 billion years and counting, and the universe at 13.7 billion years. It now appears the entire cosmos is living on borrowed time. It may be a blip within a much grander sweep of time. When, we now ask, will time end? Our lives are governed by cycles of waking and sleeping, the seasons, birth and death. Understanding time in cyclical terms connects us to the natural world, but it does not answer the questions of science. What explains Earth's past, its geological eras and its ancient creatures? And where did our world come from? How and when will it end? In the revolutions spawned by Copernicus and Darwin, we began to see time as an arrow in a universe that's always changing. The 19th century physicist Ludwig Boltzmann found a law he believed governed the flight of time's arrow. Entropy, based on the second law of thermodynamics, holds that states of disorder tend to increase. From neat, orderly starting points, the elements, living things, the Earth, the Sun, the galaxy, are all headed eventually to states of high entropy or disorder. Nature fights this inevitable disintegration by constantly reassembling matter and energy into lower states of entropy, in cycles of death and rebirth. Will entropy someday win the battle and put the brakes on time's arrow? Or will time stubbornly keep moving forward? We are observers and pawns in this cosmic conflict. We seek mastery of time's workings, even as the clock ticks down to our own certain end. Our windows into the nature of time are the mechanisms we use to chart and measure a changing universe, from the mechanical clocks of old to the decay of radioactive elements, or telescopes that measure the speed of distant objects. Our lives move in sync with the 24-hour day, the time it takes the Earth to rotate once. Well, it's actually 23 hours, 56 minutes, and 4.1 seconds, if you're judging by the stars, not the sun. Earth got its spin at the time of its birth, from the bombardment of rocks and dust that formed it. But it's gradually losing it to drag from the moon's gravity. That's why, in the time of the dinosaurs, a year was 370 days, and why we have to add a leap second to our clocks about every 18 months. In a few 100 million years, we'll gain a whole hour. The day-night cycle is so reliable that it has come to regulate our internal chemistry. The fading rays of the sun, picked up by our retinas, set our so-called circadian rhythms in motion. That's when our brains begin to secrete melatonin, a hormone that tells our bodies to get ready for sleep. Finally, in the light of morning, the flow of melatonin stops. Our blood pressure spikes, body temperature and heart rate rise as we move out into the world. Our days and our lives are short in cosmic terms. But with our minds, we have learned to follow time's trail out to longer and longer intervals. We know from precise measurements that the Earth goes around the Sun every 365.256366 days. Much of the solar energy that hits our planet is reflected back to space or absorbed by dust and clouds. The rest sets our planet in motion. You can see it in the annual melting and refreezing of ice at the poles, in the ebb and flow of heat in the tropical oceans, or seasonal cycles of chlorophyll production in plants on land and at sea. These cycles are embedded in still longer Earth cycles. Ocean currents, for example, are thought to make complete cycles ranging from 4 to around 16 centuries. Moving out in time, as the Earth rotates on its axis, it makes a series of interlocking wobbles called Milankovitch cycles. They have been blamed for the onset of ice ages about every 100,000 years. Then there's the carbon cycle. Plants capture it from the air or the sea. It finds its way into soils or ocean sediments as plants decay or as waste passes out of the food chain. It can take a volcanic explosion or a dramatic lowering of sea levels to release this carbon back into the air, often after millions of years. The processes that shape a planet like ours play only the smallest of roles in the evolution of the universe. So to glimpse time's broader arcs, we must look to cycles that govern the larger cosmos. The reigning theory is that the universe began in a sudden expansion of space, the Big Bang. With entropy uniformly low, this was the time of the tiny. Subatomic particles like quarks and leptons stirred into a hot soup. They combined into atoms, setting in motion the primordial era. The universe cooled as it ballooned, growing dim and falling into what's known as the cosmic dark ages. After several 100 million years, larger clumps of matter had drawn together. These isolated pockets of gas became dense enough to heat up and ignite. So began the era of stars. In this glorious age, the universe seeded the rich cosmic landscapes we see in our telescopes. Trillions upon trillions of stars lit up galaxies all across the cosmos. The arc of this era is defined by the life cycles of stars, which vary according to their sizes. Stars shine because gravity crushes matter into their cores. The energy released pushes outward and balances the inward force of gravity. This battle between energy and gravity is raging in stars all around the universe. But in large stars, about 10 million years after their birth, gravity begins to gain the edge. When the mass concentrating in the core of the star reaches a critical threshold, the core collapses in on itself. The energy released in the collapse causes the star to explode in a blast of light and debris that's visible across the cosmos. In the wake of this supernova, shock waves can cause nearby clouds of dust and gas to collapse and ignite to form generations of smaller stars like our Sun. A byproduct of star formation, solar systems form in the collapse of the surrounding solar nebula. The life cycle of planets, especially those in close, is tied to that of their parent stars. As stars like our Sun age, they grow hotter and more luminous. Billions of years from now, that will spell the beginning of the end for our home planet. As raging solar winds begin to blast away at our atmosphere, surface water will gradually disappear, rendering Earth uninhabitable. Finally, the Sun will begin to swell, growing so large that it actually envelops the Earth. Friction with the Sun's outer edges will cause this once blue world to gradually spiral inward. Unless they are large enough to go supernova, most stars end their lives in more of a whimper than a bang, as shown in this gallery of dying stars captured by the Hubble Space Telescope. In time, solar winds push their outer layers so far out, they blossom in spectacular displays. That's just what happened about 12,000 years ago to the star that spawned the famed Helix Nebula. On the inside, spokes of denser gas stubbornly resist the star's relentless winds. The star itself is now a dim, cooling remnant called a white dwarf. It's the size of Earth, but about 200,000 times more dense. This is likely what's in store for our Sun. A distant civilization may scan it for planets, but by then they won't see Earth. This battle between energy and gravity repeats in every corner of a galaxy like ours, with gravity drawing gas clouds into stars, and stars burning themselves out on a variety of timescales. In time, though, as the mass of the galaxy collects in successive generations of small stars, it will grow dimmer and dimmer. Some galaxies will see a temporary rebirth if their mass gets stirred up and combined with another. That's what's destined to happen to our Milky Way. At just about the time our Sun begins to swallow our planet, any remaining Earthlings will see the stars of the Andromeda Galaxy looming above the plane of our Milky Way. As shown in this simulation, the two are likely to tear each other apart. If it's a direct hit, the stars in both galaxies will gradually join together in a gigantic galactic puffball known as an elliptical galaxy. All the turbulence of the merger could stimulate a wave of new stars being born, reinvigorating the new, larger galaxy. Dust-ups like this, in which galactic neighbors merge, will be common as the era of stars moves into its later stages. You can see evidence of this now, out in the huge voids of space between filaments of galaxies. These voids are like ever-expanding bubbles. Where the bubble walls touch, you can see filaments of galaxies. As the bubbles grow, the filaments will stretch and break. The distance between galaxies will widen at a faster and faster pace. Eventually, no matter where you are in the universe, you will see only a few isolated clusters of galaxies huddled together, with little connection to anything else, and few clues to how they got there. At more distant reaches of time, this will begin to transform these small outposts. Over time, chance encounters between objects will perturb their orbits, sending some toward the center of the galaxy, and others out into the void. In this way, galaxies may gradually evaporate, with ever denser concentrations of matter accumulating in their cores. As that happens, the universe begins to take on a new character. Welcome to the degenerate era, in which the universe is populated by red and white dwarf stars steadily cooling, and by the charred remains of supernova explosions, neutron stars. Even though these dead stars have used up their nuclear fuels, they continue to produce small amounts of energy. They scoop up and annihilate dark matter particles that manage to stray into their grasp. Here is where cosmic evolution slows to a crawl. It's expected that protons, the building blocks of all atoms, will slowly degrade, turning into subatomic particles that then decay into photons. All the protons in existence date back to the early moments of the universe. Their eventual decay will mark the end of the degenerate era. Around 1 billion years after the Big Bang. That's a 1 followed by 40 zeros. Our picture of what happens after that depends on what we learn in the coming years beneath the border of France and Switzerland, in one of the largest physics experiments ever undertaken. 100 meters underground, the Large Hadron Collider was built to accelerate particles in opposite directions through a giant ring 27 kilometers around. When they reach nearly the speed of light, scientists will bring them into ferocious collisions. One goal: to define the final time horizons of our universe, as well as the final moments of its most persistent objects. Black holes, ranging from millions to tens of billions of times the mass of our Sun, occupy the centers of large galaxies today. As those galaxies age, over trillions of years of time, much of their mass will spiral toward the center and into the jaws of ever more ravenous black holes. Conceivably, these black holes could end up weighing as much as a galaxy. But when they finally stop growing, will they too be subject to the ravages of time? According to the physicist Stephen Hawking, the answer is yes. He proposed a theoretical process of decay that scientists are hoping to test in high-energy particle collisions at the Large Hadron Collider. The idea is that throughout our universe, particles of opposite charge constantly well up in the vacuum of space. They normally destroy each other. But when this happens at the event horizon of a black hole, one particle can be pulled in while the other escapes. That has the effect of slowly siphoning energy and mass from the whole. If this is true, then even black holes are eventually doomed. But finding out for sure is not easy. Creating a micro-black hole, it seems, will take more energy than any Earth-bound collider can pack. That is, unless there's more to nature and to gravity than we've thought. The key lies in whether the universe we know is part of a more complex cosmic reality beyond the 3 spatial dimensions, plus time, that we experience in our everyday lives. We may be like an insect living on the 2-dimensional surface of a pond, unaware of the deep and complex reality below it. It may be possible that an unseen extra dimension could intersect our world on an extremely tiny scale. According to some scientists, when particles collide at very high energies, the additional gravity needed to create a micro-black hole could come from the extra dimension. They'll know a black hole is there when they see the shower of particles predicted by Hawking's theory. Its presence will open a brief window to a deeper cosmic reality, while shedding light on the ultimate future of our universe. Based on Hawking's theory, a black hole observed today will take its last gasp when the clock strikes 10 to the 100th years from now, a number known as a googol. That's the end of the universe as we know it. But look beyond that to say 10 to the googol, a googolplex years. If you wrote all the zeros in that number in tiny 1-point font, it would stretch beyond the observable universe. Will the great arrow of time have come to rest by then? Not if modern theories are correct. They hold that our universe is part of a much larger cosmic cycle of birth and death, with whole new universes coming into being in the space beyond our own. The time horizons of our universe may well be a blip in this grander scheme of things. Back to Earth now. We are products of the great era of stars and witnesses to its great spectacles of gravity and energy. No doubt there are other beings somewhere out there who are attempting to comprehend the universe. They too may invent the idea of time and develop their own theories on where it's all leading. Their discoveries and ours will not survive the entropy at work in the universe, as we all go the way of the stars, and as our universe gives way to grand new eras in the life of the cosmos.
Checking out traffic this morning along the Kewy Gardner, Guy Valentine.
It's a bit of a battle for drivers without cover. I'm talking if you don't have any shade, you're fighting some pretty bright sunshine.
Also caution on Highway 7 going east of Michigan.
And northbound Don Valley Parkway on the ramp to eastbound 401, we've got a disabled vehicle.
June the 14th, 2002. It was just another busy workday with all the usual hustle and congestion. With all the close calls and near misses that people all over the world have come to accept as the normal level of risk in everyday life. But on that day, high overhead and behind the sun, what no one saw coming, what no telescope on Earth was able to see against the blinding light, was an asteroid big enough to destroy an entire city. From behind the sun, asteroid 2002 MN came hurtling towards Earth, faster than a speeding bullet. It shot past, less than a third the distance to the moon, and nobody saw it, until 3 days later, when the rock emerged from Earth's shadow into the night sky, going away.
It looks like the Earth just dodged a bullet. Actually, it was an asteroid. Scientists say it blew by last week at a distance they describe as a close shave.
The airline industry would call this a near miss. Scientists who study asteroids and comets called it a problem.
The threat of asteroid impacts on the Earth is very real. We know that throughout history this has happened. The craters we see on the moon are examples of the kind of impact history that the Earth has had. But it also happens very rarely. So it's a very unusual kind of hazard. It's a hazard in which the risk in any one year is very low, but it does happen, and if it really did come about on our watch, it could end civilization.
These cosmic bullets originate on the far side of Mars, in the main asteroid belt, where a bracelet of celestial debris circles the sun. Millions of rocky fragments, building blocks of a planet that never quite came together when the solar system was formed. What's often depicted as a busy cosmic junkyard is actually more like a big empty speedway. The rocks are far apart and moving very fast, ranging in size from pebbles to boulders to rocks the size of Mount Everest. Occasionally, the tug of Jupiter's enormous gravity drags an asteroid off course, causing it to crash into another asteroid. Some veer away into new orbits that cross the paths of Mars, Earth, Venus or Mercury. Another ring of debris called the Oort cloud is the source of most comets, which are big, rocky ice balls that orbit the Sun and cross the paths of the inner planets. All the inner planets and our Moon bear the scars of numerous asteroid and comet impacts.
We do get hit all the time by pieces of debris from asteroids and comets. In fact, 40,000 tons of cosmic debris plummets into the atmosphere every year. We see them every night as shooting stars. They don't hit the Earth very often, but when they do, clearly it isn't just going to be a matter of a shooting star seen in the sky. So it is inevitable. It's only a matter of time before the next big one hits us.
Even small rocks can make a big impression. In 1908, about 2,000 square kilometers of Siberian forest were instantly flattened as an asteroid exploded near the Tunguska River. The impact site was so remote, researchers had to mount a wilderness expedition just to find the place. When they arrived, there was no crater. Paintings, based on eyewitness accounts, described a fireball. A horrendous explosion in the sky.
Didn't actually come crashing down to the ground. It exploded maybe 5 to 10 kilometers up in the atmosphere, and that made a big blast wave in the atmosphere, and that is what did the damage.
All this was caused by a relatively small asteroid, somewhere between 50 and 100 meters across. Roughly the same size as asteroid 2002 MN, the one we couldn't see coming. Tunguska's 2,000 square kilometer blast wave would have leveled London. But as bleak as the thought of cosmic collision may be, there is at least a glimmer of hope.
One of the special things about the asteroid impact problem is that unlike the weather or earthquakes or other natural hazards, we, at least in principle, we could do something about it.
And when we know one's coming for us, our claim is that the technology is available today to stop it.
On the Earth, we've got active geology, we've got volcanoes, we've got earthquakes, we've got continental drift, we've got rain, we've got wind, we've got storms, we've got snow. All of those things erode away craters, and that, in some ways, actually fools us into thinking that indeed the Earth doesn't get hit as often as it actually does.
Counting craters on the Moon and then estimating how often the Earth gets hit can be a pretty sobering exercise. One scientist who made that kind of calculation was astronomer Ernst Öpik, who published his impact estimate back in 1951. The general public, however, paid little attention to the science or the implications. But one individual who did take the issue to heart was Lembit Öpik, the astronomer's grandson, who got himself elected to Parliament.
My grandfather is the reason why I carried on in politics, what he initiated in science. In essence, he was a pioneer. He saw the danger of asteroid and cometary impacts with the Earth, and he had the courage to speak up about them. And he did that at a time when it wasn't really taken seriously, in the 1950s and 1960s.
After years of pushing and prodding, Lembit Öpik convinced the British government to commission a comprehensive scientific study of the asteroid and comet threat. The expert conclusion was, the threat is indeed real.
The government has set up a task force to examine the risk of an asteroid hitting the Earth.
Still, skeptical politicians might want to get on the bus and take a trip to the Natural History Museum. Ask any schoolchild who's been there recently, and you'll hear a fascinating and truly scary tale about what happened to the dinosaurs.
The dinosaurs were alive here. They were dead when this sediment was deposited, and this layer is one of the most unique layers in Earth history.
In 1980, the discovery of iridium beside a layer of clay which marked the end of the age of dinosaurs led Lewis and Walter Alvarez to publish a theory that a huge asteroid or comet had hit the Earth 65 million years ago and wiped out the dinosaurs. But for this concept to be confirmed, there had to be a crater. There may be tons of dinosaur bones in these dry canyons, but where on earth was the big crater? Just the kind of mystery a budding young scientist would love to solve.
When I went back to...
Off the coast of Mexico's Yucatan Peninsula, Dr. Alan Hildebrand investigated a huge gravity anomaly discovered by oil drillers back in the 1950s. Put that together with a semicircular magnetic anomaly, and you get a massive crater, 180 kilometers across, near a little village called Chicxulub Pueblo. Most of the crater is underwater now. Erosion and continental drift have covered the visible evidence. But 65 million years ago, this was ground zero.
This object would have fallen through the atmosphere in just a few seconds. Just going through the sky, it would have been brighter than the sun. As soon as it contacts the surface of the shallow sea in Chicxulub, of course, it starts propagating the shock wave down into the planet, and it keeps pushing into the planet, and it only gets stopped maybe about 30 kilometers down. The pressure wave would have traveled around the entire planet in the atmosphere. You could have heard the impact on the other side of the planet. The giant impact fireball rising out of the hole, it would have risen, say, 10,000 kilometers above the surface of the planet. Near the impact site, it would have been so hot, it would have evaporated the clouds and been hot enough to make the forest, even a green forest, begin to burn.
For Alan Hildebrand, finding that crater pretty much clinched the argument. Planet Earth had been all but sterilized by a rock the size of Mount Everest.
3/4 of the species of large animal life went extinct.
We have made the case. We've got the qualitative information and we've got the statistics to show that there is a very serious risk. If you wanted to save planet Earth from cosmic disaster, where would you find people with all the right stuff to do the job? Well, Houston, Texas might be a good place to start looking. This town has that rarest of breeds, the space cowboy. Houston is home to NASA's Johnson Space Center, where rocket science is a way of life and astronauts learn their trade.
If you could roll me 90, then go down. I'll come in on my side.
Behind a swimming pool big enough to swallow an apartment block, you'll find a small research lab where the rocket engine of the future is being built and bench tested.
Yeah. Mm-hmm. Very nice. Question is, how big is the plasma going to go from here to here?
Dr. Franklin Chang Diaz is one of the lead researchers, as well as an astronaut with 7 shuttle missions under his belt.
And in fact, there was a time in one of my flights where we got hit by very tiny micro meteorites, perhaps, or some sort of orbital debris, which made little tiny dents or little craters in the windows of the shuttle.
Well, that tube is welded. Yeah, I did it. We already welded it. Yeah, I did it.
First-hand experience with rocks in space gave birth to a new idea and a dual purpose to Chang Diaz's work here. His rocket engine has been developed for long-distance missions to Mars, or as far away as the icy moons of Jupiter. But it could also be used to push a dangerous asteroid out of harm's way.
I am concerned enough to think that we need to not waste time arguing about it as to whether it's real or not. I think we need to move ahead and do them.
Well, I'm wild and I am free. Come on, baby, you belong to me. Sweet kiss makes my passion start. Well, I'm wild and I am free. Come on, baby, you belong to me. Sweet kiss makes my engine start. The way you move, you own my heart. Sweet kiss makes my engine start. The way you move, you own my heart.
If this is a threat which has a very low probability, all it takes is one, and we are history.
But before we can send a spacecraft chasing after a rogue asteroid, we have to know where to look for it. In the American West, if you drive across the desert to the White Sands Missile Range in southern New Mexico, you'll find the most powerful and effective asteroid hunter on Earth. Scientists here have tested everything from rockets to the very first atomic bomb. Today, across the valley floor from the Trinity bomb site, the US Air Force has installed one of the world's most advanced telescopes. This state-of-the-art technology was developed by MIT's Lincoln Laboratory as part of the Star Wars anti-missile defense system. These may not be the world's biggest telescopes, but they clearly are the best when it comes to finding deadly rocks in space. This is LINEAR, the Lincoln Near-Earth Asteroid Research Facility.
On a given night when we scan the sky with this, we'll find perhaps 10 to 12,000 moving objects in the sky. Now, most of those are main belt asteroids and as such don't represent any danger to Earth. But on the other hand, something like half of those will be brand new discoveries, and buried in there will be one or two near-Earth objects.
Because the Earth rotates, the sky is always moving overhead. To get a clear picture of an asteroid, you have to make the sky stop moving. And you do that with a telescope that can track or follow the stars. This way, you can take time-lapse pictures that isolate the blur of fast-moving asteroids against a crystal-clear sky. It then records these pictures like a TV camera on a computer chip that has 20 times more detail than the picture you're now watching. The LINEAR computer deletes previously known stars and planets, leaving a less cluttered time-lapse sequence of the new discoveries. At the end of each night shift, LINEAR's thousands of new discoveries are emailed to the International Astronomical Union's Minor Planet Center at Harvard University. A team of only 3 scientists must cope with the avalanche of new sightings, searching for potentially hazardous asteroids or comets. Computers make a rough calculation of an asteroid's orbit, but it's up to Brian Marsden to estimate the level of risk.
They may be reporting 50 or 60,000 observations from one night, and it takes a while to get through that. But so we look first at the fast movers and see if there's anything interesting there.
H is equal to sine delta. We do sometimes get close to
70 or 80,000 observations a day, almost one per second. There are some days when we effectively have one observation per second.
Even with fast computers, Marsden's team can make only a preliminary calculation of each asteroid's orbit. 5 shots in one night cover only a tiny segment of an asteroid's orbital path.
You can't solve for the orbit completely from that, but the fact that you're seeing motion over a half an hour or an hour, something like that, does allow us to get a partial solution for the orbit.
Refining the orbit gets complicated. When 2002 MN shot past, its trajectory was warped by Earth gravity, and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, had to add that to their calculations.
Here's an animation I put together of the asteroid last year, which was discovered after it passed by the Earth.
An elite team of mathematicians and celestial mechanics is now working full-time on a computerized warning system.
Our orbit animation, you can see how when it returns out to the asteroid belt, the close approach to the Earth has changed its orbit, and it's no longer returning to the same place it started.
Because 2002 MN will circle around the Sun and come past us again, the NASA Orbital Mechanics team will have to adjust the calculation in order to know whether it will ever pose a danger to Earth at some point in the future.
So here we've zoomed in on the Earth-Moon system and we're looking down. You can see how close it came to the Earth. It went over the top. And how you can actually even see the bend in the trajectory. So it's a great example of how a close approach to the Earth, or in fact any planet, can be used to, or can significantly change in orbit.
To know where an asteroid is likely to be in the future, you need a model of the solar system. Mechanical models that show the relative motions of the Sun and planets have been around since the early 18th century. They're called orreries. What the celestial mechanics at NASA had to do was create a new digital model. One that includes the gravitational attractions of all the planets and the Sun, and all the other forces that can affect where an asteroid might go.
You just compute what forces are acting on this particular asteroid from all the planets and many of the minor planets in the solar system, and then we can actually trace the motion of that object around the solar system for hundreds of years.
For scientists, the acid test of their mathematics came when a strange new comet raced toward Jupiter. A stream of cosmic bullets that would shock and amaze millions here on Earth. In the spring of 1993, the eyes of the world turned almost in unison towards a doomsday rock like no other. From the far side of the solar system, it flew in a death spiral toward the largest planet. Gene Schumacher, his wife Carolyn, and their colleague David Levy had discovered an odd-looking streak of light that turned out to be a fractured comet. 21 large chunks of icy rock and cosmic dust heading towards Jupiter.
We knew we had something very unusual. It was so unusual we were a little unsure just what we were dealing with.
NASA asked Paul Chodas and his team to calculate the orbit and predict whether this new comet would actually hit Jupiter.
And it started off at some 60%, and before long it was 90%, and this was a year before impacts. As the impacts approached, we continued to predict not just the impact probability, which went very high, but where and when the comet fragments would hit the planet. And it was a prediction months in advance, and as we got closer and closer to the impacts, I kept wondering, well, is the math right? Will this actually happen the way it was predicted?
A giant comet is on a collision course with Jupiter.
Everybody on Earth who was paying any attention wanted to see if the comet would actually hit Jupiter.
We have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
NASA's Hubble Space Telescope set its sights on the planet, and the pictures of what happened next were truly stunning.
Right there! Oh! Get it! Wait. Oh,
And then the impacts occurred. We were within minutes of getting the right answer on the time of impact, and the location of impact turned out to be just right.
Over the next week, 20 more fragments of the comet crashed into Jupiter, some leaving scars as large as the Earth.
Bang on its cosmic schedule, the comet's first impact was recorded by NASA within the last hour.
When fragment G slammed into Jupiter, releasing an amount of energy equivalent to about 6 million megatons of TNT.
In the wake of SL9, a group of concerned scientists gathered in Italy for a brainstorming session. They created a brand new international organization called the Space Guard Foundation.
Okay, I'm going to join.
To promote the discovery and study of near-Earth objects.
Some people imagine that there are lots of astronomers out there scanning the sky looking for incoming comets and asteroids, and that, of course, is not true. In fact, until recently, there was hardly anyone out there looking.
It's going to glow for about a half an hour and set everything on fire around you.
But whose job is it to defend planet Earth? Weapons scientists from the United States and Russia had already held a series of meetings and came up with their own ideas about how to deal with the impact threat.
You blow off some material, you get a reaction in this perpendicular direction.
The military establishment under Star Wars had created a whole lot of devices, or at least concepts, for weapons in space and devices in space. And in the early 90s, when the Star Wars program was looking a little bit iffy, I think there was some motivation for them to try to apply their technology to this newly discovered hazard from asteroids and comets.
The military approach to the problem proved to be controversial. The notion of sending nuclear weapons into space generated an immediate backlash.
Edward Teller was proposing that we blow up an asteroid to show that we could protect the Earth, and I thought that was a pretty crazy idea. Blowing up an asteroid with a big bomb has a lot of problems associated with it, violating treaties, taking a single asteroid and making a swarm of smaller asteroids. It seemed like it was more interest in bombs than it was a serious interest in defending the planet. For NASA, on the other hand, NASA obviously is the natural agency to discover the threat and the objects, but they say no, planetary defense, that's a military obligation and not an obligation of NASA.
Not NASA, not the military. Just when it seemed planetary defense was nobody's job, a tiny speck in the sky would set off doomsday alarms around the world. On a winter's night, the 6th of December 1997, a dim streak of light moving through the constellation Cancer was captured by a telescope in the Arizona desert. Big enough to destroy civilization as we know it, asteroid 1997 XF11 seemed to be heading towards Earth. The initial sighting by the Kitt Peak Observatory in Tucson, Arizona, was relayed to the Minor Planet Center at Harvard University in Cambridge, where a computer made the first rough calculation of the orbit. They were pretty sure it would miss the Earth on this pass, but it would be coming round again, and it looked like there could be a problem in 30 years.
There were indications of close approach to the Earth in 2028. That was about 45,000 kilometers, which really was rather close.
With only a handful of sightings, the orbit calculation remained very rough. It was hard to tell where this rock was going. So Brian Marsden posted a bulletin asking astronomers around the world for more observations before the rock became too faint to see.
I was saying, hey, get your big telescopes onto this. On the one hand, we're only going to be able to observe it for another month or so. We want to improve the orbit calculation and find out exactly how close it is coming.
But one line in the bulletin said that the chance of a collision was small, but it was not entirely out of the question. Within hours of the website posting, reporters discovered XF11, and doomsday headlines screamed around the world. Because the close approach in 2028 would put the asteroid nearest to Europe, London newspapers focused on the exact moment life on Earth might possibly end.
Pictures of it on the internet show it as a tiny moving blob. Scientists have calculated its path in the year 2028.
Watch very carefully. September, October the 28th, the two coalesce.
But at NASA's Jet Propulsion Laboratory in California, the orbital dynamics team thought there must be some mistake.
Asteroid's orbit was affected by it. To my great surprise, when we ran our software, it said that the probability of impact of this particular asteroid in 30 years was essentially 0.
As it turned out, the end-of-the-world asteroid would miss the Earth. That big rock in space posed no threat after all. A frantic hunt through the archives at NASA had turned up photographs of XF11 taken 8 years earlier.
And as soon as those were placed into the orbit determination process, they confirmed the fact that there was no chance that it could hit the Earth in 30 years.
The public at large was not understanding uncertainty in this. They wanted an immediate answer. Is it going to hit us or not?
But people were paying attention. One side effect of the false alarm was that public and political awareness of the threat had been raised. 2 months after XF11, new hearings were held in Washington, and NASA was told to speed up the science of asteroid detection. Finally, it seemed, there was a political will to do something. Congress gave NASA a 10-year deadline to search the skies and get a fix on the largest of the doomsday rocks. They called it the Space Guard Survey. While astronomers geared up to search the skies, Hollywood was going into overdrive.
I would go to every dinner party and I would say, are you aware what would happen if a comet was actually on a collision course with the Earth?
Oscar-winning screenwriter Bruce Joel Rubin was hard at work on the remake of a sci-fi classic. The new film, called Deep Impact, would be a Steven Spielberg production.
When we arrived at our hotel in New York, the porter was so incredibly careless with our bags. And the room they gave us, it was beautiful. A broom closet. But the worst part was the shower. My wife drying herself with the Egyptian cotton towel shower curtain defined that whole vacation for her. Don't just visit New York.
Visit TripAdvisor New York. With millions of reviews, a visit to TripAdvisor makes any destination better.
An army of scientists work desperately to build this giant rocket, this modern Noah's Ark, to carry a few picked survivors of our doomed civilization.
I think the thing that was hardest for me was the realization that people would have to be chosen to survive.
Let's take the ship away from them! Come on!
Probably a very, very small percentage of human beings would be left on the Earth able to survive something of the intensity of the comet that hit and destroyed the dinosaurs. So I felt making this movie is not just a mission to tell a good story, it's to change minds. It's to let people go, this is something real. This can happen to us. This movie is a wake-up call. It's not just a Hollywood movie, it is pointing at you.
As Hollywood released Deep Impact, telling the world in no uncertain terms that cosmic collisions were no longer just a cosmic joke, real-life professional asteroid hunters were making movies of their own. But instead of using cameras, they worked with delayed Doppler radar. Take the same technology behind a police radar system, jump the power to 400,000 watts, and you've got NASA's Deep Space Network with huge multi-dish systems like the Goldstone tracking station in California's Mojave Desert.
This is the main room of the pedestal of DSS-14.
The first time radar astronomer Stephen Ostro bounced a signal off a rock in space, a wobbling blot of pixelated data bounced back. What looks like digital gibberish spoke volumes to Steve Ostro.
Radar really does three things at once. One, it works at long wavelengths, so you're sensitive to structure on large scales and metal concentration. The other is you can make pictures. And you can't do this from the ground in any other way. You make pictures of objects, and then we take a sequence of pictures, and we go through a computational process to produce the 3D models. That's the second thing. The third thing is that it makes very precise measurements of distance and speed.
When the 1,000-foot radar dish at Arecibo in Puerto Rico bounced a beam off an asteroid called Castalia, the data was translated into a 3D computer model. The very first radar movie showed how Castalia spins and revealed that it was actually two massive chunks of rock held together by weak gravity. Every time they made the trip to Goldstone for a new radar target, Ostro and his team were like kids reaching into a box of chocolates. They never really knew just what they would find. Asteroid Cleopatra, shaped like a dog bone, was roughly the same size as the state of New Jersey and was made almost entirely of metal. Echoes from asteroid Toutatis produced images of a rocky, cratered surface and a wobbling, tumbling spin.
Every single one of these objects that we've made a shape model of is very different. This is Toutatis.
From a telescopic smudge of light to a 3D shape model, radar gave them physical details and the first clear idea of what asteroids are really like. In the year 2000, the radar movie crew developed a dark and mysterious new image, asteroid 1950 DA, a big rock that gave everybody a bit of a shock.
Once we got the radar data, we began the normal process of just seeing how far in the future we could predict this thing before the uncertainties in the orbit blur out. And in this case, we could go over 880 years into the future. And what was startling about that case was the impact probability turned out to be non-zero.
Non-zero means there is a chance this rock could hit us. On March the 16th, in the year 2880, 1950 DA will cross the Earth's orbit. Will it hit us? The odds? 1 in 300. If 1950 DA does hit the Earth, the most likely point of impact would be at sea. Of all the big asteroids discovered thus far, this is the most dangerous one we know. Eric Asfaug and Stephen Ward have created a computer model of the impact.
Yeah, it's kind of funny how this started. It was with the movie Deep Impact, and I was getting phone calls. Lots of people were getting phone calls about the movie, whether it was accurate, the big cresting tsunami coming across.
The concept here is that this asteroid, which is about 1 kilometer across, will hit the ocean at 17,000 miles per hour, and it'll blow a hole in the ocean about 19 kilometers across and all the way to the bottom. And so when this huge hole of water gets blown into the ocean, the water will run back in again, and it overshoots and it collapses and overshoots many, many times, and each time it pumps out a wave. So it starts out hundreds of meters high, comes ashore on the coast of North America at about 50, 60 meters. Up toward Canada, Grand Banks, it's about 40 meters. 20 meters here in the coast of South America, and about 15, 20 meters all the way over to Europe. These waves would run inland about 4 kilometers. So pretty much everything within 4 kilometers from the beach would be covered up repeatedly. And so we'd pretty much be wiped away like you're scrubbing the floor. You know, just scrub like this, and it's pretty much all be carried back out.
In February 2001, a NASA spacecraft called Near Schumacher made the first ever landing on a chunky, pockmarked rock named after the Greek god of love. Asteroid 433 Eros is 33 kilometers long and 13 kilometers wide, one of the largest near-Earth asteroids. The pictures were spectacular. The data will take years to process. Proving that they could land on an asteroid was a major achievement, but in the end, they still don't know much about what's inside. How dense? How tough? How brittle or crumbly is it? What would happen if they gave it a good shove? The surface appearance of any dark and mysterious object can be very deceiving.
So these two spheres, as far as I can tell, have exactly the same mass, the same compressibility, the same color. If I were a spacecraft orbiting these and these were asteroids, I'd be very hard-pressed to tell which was which. Yet, if I dropped them from a height, and only one of them bounces, really illustrates the fact that one of these responds elastically and one of these responds like a lump of clay. And it's critical to really go and find out what's inside before we even start thinking about moving these things around.
When a 3D model of the asteroid Castalia got smacked in a computer simulation, a problem occurred. An impact with the same energy as the Hiroshima bomb turned Castalia into a pile of rubble, but did not deflect its trajectory in any significant way. But there are other ways to apply force to deflecting an incoming asteroid. Using the power of the sun to push dangerous rocks out of the way may not be so far-fetched after all.
This is a typical near-Earth asteroid. Its name is Galevka. It's about half a kilometer across. It's a hazardous asteroid. Its most likely fate is going to be to strike the Earth someday, thousands of years from now.
Modern-day researchers like Eric Asfaug say the idea of a giant orbital magnifying glass to burn space rocks could work.
You create a vapor plume in one direction, and that starts the asteroid moving in the other. It's a very gradual process. It's not going to happen instantaneously. You need to know where this guy is 100 years or 50 years ahead of time. But if you do, you've got all the time in the world for a satellite to sit there, no human intervention whatsoever, and it'll gradually shove the asteroid into a different orbit, and it'll miss the Earth.
Some of the technology to do this already exists. Take an inflatable parabolic antenna the size of a tennis court, convert it to a solar collector, and use it to focus sunlight on an asteroid. The Russians have built and are testing a giant sail that captures the minute pressure of sunlight. Just attach the sail to an asteroid and let the rock hitch a ride to someplace else. But using the sun to save the Earth means waiting for nature to do the work. If we don't see an asteroid until the last minute, solar power would be too little, too late. A nuclear electric plasma engine could push an asteroid out of harm's way. The rocket technology at this NASA lab in Houston, Texas, could provide the power for a space tugboat. A group of astronauts and aerospace engineers is designing the B612 mission to prove that asteroid deflection can be done with existing technology.
These are rockets that have very tiny amounts of thrust, but they are so frugal in the use of propellant that we can keep the rocket going for periods of the order of a year.
Building a better rocket engine is only the first step. Figuring out how to latch on to an asteroid, point it in the right direction, and push without losing control is the really tricky part. After years of research, NASA finally had it, the first complete draft of a plan, a demonstration mission, to save the planet.
move the asteroid off the impact with the Earth 10 years later so that it misses the Earth, and not just miss it randomly, but miss it very precisely so that we don't simply pass on the problem to our grandchildren.
Midway through 2003, the SpaceGuard survey had reached the halfway point. A little more than half of the kilometer-sized near-Earth asteroids had been located, and the news was mostly good.
For the 60% that we have already found, I can tell you that there is not a single one that poses a danger. For the 40% that we have not yet found, I can tell you nothing. One could hit tomorrow. Not very likely, but until we've found them and cataloged them, we won't know.
But finding the really big asteroids, those 1 kilometer monster rocks capable of ending human civilization, is only the first part of the challenge. There are an estimated 50,000 smaller asteroids that are big enough to cause tidal waves or destroy vast regions of the Earth.
A 200-meter asteroid happens maybe once every 10,000 years, but that's like 600 megatons to 800 megatons exploding in one place.
Recall the small 60-meter rock that exploded over Siberia in 1908? Well, even though it could have destroyed a city like London or New York, rocks that small are not included in the current SpaceGuard survey, meaning no one is officially looking for them.
Which, of course, is the same thing as saying that chances are enormous that a Tunguska-sized object will find us before we even see it coming, as happened in 1908. That is likely to happen nowadays, that we won't see it coming.
There has been talk of expanding the search to include smaller asteroids. It'll take more and bigger telescopes and, of course, more money. But until we do, we'll have no idea where those city-killer rocks are.
Evolution on Earth has proceeded in part because every so often a global catastrophe comes along, pushes the reset button, and new things happen.
It wiped out the dinosaurs 65 million years ago, and at the time, we mammals were just furry little creatures burrowing around in the ground, and an asteroid or a comet impact took out our principal competition.
I guess we are saying implicitly, if not explicitly, that we want to do away with that natural cycle.
We've had enough evolution. We like ourselves on the top of the ladder. And we can do something which will change cosmic evolution from this point forward in terms of life on Earth.
Dinosaurs ruled the Earth until a big rock wiped them out. The question is, will another rock do the same to humanity?
Let's get a couple good pictures here.
Humans are the first species with the potential to block a doomsday rock and switch off the evolutionary reset button.
People very often say, look, you're just a doomsayer. You think that these awful things are going to happen. I'm not that way at all. I'm entirely optimistic. The way in which I view asteroids and comets and the possibility of them hitting the Earth is that it's a great challenge. Thank goodness we've realized the hazard and the danger before the next one happens. It's given us time, we hope, to do something about it.
Scientists can study the sky and find the dangerous rocks ahead of time. Astronomers can do the math and predict the orbits. People have the desire and the right stuff to do the job. There's a whole new field of science that could give humanity an option the dinosaurs never had.